This is a recording of the presentation of the paper Removal of Small Weight Stopping Sets for Asynchronous Unsourced Multiple Access. The presentation was first held at the ISIT in 2025 in Ann Arbor. My name is Frederick Ritter and I am with the Communications Engineering Laboratory at the Karlsruhe Institute of Technology. The Internet of Things poses many challenges from a communications engineering perspective. Some of them are the large number of transmitters, which are often only active sporadically, these short messages that these transmitters do send if they are active, and then the limited energy that is often available because many of these transmitters are relatively small devices which may even be battery powered. Now, the combination of these challenges makes coordination between these users even more challenging, because any amount of resources we invest in coordinating the users is immediately a relatively large overhead compared to these very short message lengths, and that is then immediately relatively bad if we think of the limited energy available to these small transmitters. So, if we are trying to implement a protocol for something like this, what we may look to is something like the two-step random access in 5G. Here, each user first transmits a preamble, and then without waiting for an acknowledge from the base station, it immediately transmits its data. And the preamble uniquely defines in which physical resources the data is transmitted. This means that if the preambles are sufficiently orthogonal for the base station to recover each preamble of each user, the base station then also knows where to look for the data, and it can also recover the data. Now, if we increase the number of users, we will inevitably have some collisions in these preambles, and then we will also have collisions in the data resources. If we can no longer increase the number of preambles, we have to somehow deal with these collisions, and one method of doing this is with coding. Now, as long as the number of users in the system is reasonable, the most probable event will be the collision of no users. But the next most probable event will be the collision of 2 users, and the collision of 3 or more users will be increasingly less probable. So, for a very simplified channel model, we'll be looking at only 2 users that both send BPSK symbols over a channel which adds these 2 symbols together, and then we receive the sum. We do not have any noise in our channel model because this is a very simplified channel model, but what we do not ignore is the fact that these 2 users are uncoordinated. In the framework of unsourced multiple access proposed by Polyansky in 2017, this means that the 2 users are using the same code C. If both users use the same code, this also means that the receiver can no longer attribute which code word was sent by which user, but it can only recover the set of transmitted code words, which we call L of Y. The error probability is then also defined per user, namely the probability that for a given user, its transmitted code word is not in this recovered list L. You may have also noticed the delay tau in our channel model. We specifically require this delay tau to be larger than 0, because if the delay tau is 0, the capacity of this binary adder channel is not achievable with linear codes. If it is greater than 0, it is achievable. For the details on why this is the case, I refer to the cited paper, but we will be using linear codes, so we require the delay tau to be strictly greater than 0. The linear codes we are using are low-density parity-check, or LDPC codes for short. They're defined as the null space of a sparse parity-check matrix H, and this parity-check matrix can also be represented as a tannograph. The tannograph consists of variable nodes, which represent the columns of the parity-check matrix, and check nodes, which represent the rows of the parity-check matrix. Now, some very important structures in this parity-check matrix are the so-called stopping set. A stopping set is a set of variable nodes such that each check node connected into this set has 2 or more connections into this set. The significance of these stopping sets is that if we are transmitting over binary erasure channel and all variable nodes in a stopping set are erased, and we use iterative decoding, then this iterative decoder cannot recover these erasures, even if an ML decoder maybe could recover them. However, of course, in this case, we are not in a binary erasure channel, but we are decoding the transmission received from 2 users. Now, if we have 2 users, we need 2 tanographs, and if we have the delay tau, we have to shift these 2 tanographs accordingly, and then we connect them with what we call multiple access nodes. These multiple access nodes essentially implement the channel constraints that these 2 users sum up for the receiver. However, now we can actually use a decoding that is very, very similar to binary erasure decoding, because if one user sends a +1 and one user sends a -1, the receiver finds a 0. If it finds a 0, it does not know which sender sent the +1 and which sender sent the -1, which is effectively like an erasure. This means if we use binary erasure style decoding, iterative of course, then we are very interested in the stopping sets in this joint graph. And this is the smallest stopping set that you can ever find in such a joint graph. It is called the 4 degree 1 variable node stopping set. We're of course interested in the smallest stopping set because it has the highest probability of being erased. In this case, if both users send their code words with the same probability, the erasure probability of this stopping set is 1/4. While it is relatively simple to eliminate such stopping sets for any given delay tau, in the paper we look at ways to remove these delay stopping sets for all delays tau greater than 0. A technical note on the side, I'll be talking about degree 1 variable nodes from here on out quite a lot. Whenever I say degree 1 variable node, I mean the degree of the variable node in the tenor graph. Of course, the degree 1 variable node may have an extra connection to an MN. In this case, it technically has a degree 2 in the joint graph. However, I will be further referring to it as a degree 1 variable node. Actually, this extra degree in the joint graph is the reason why we can use degree 1 variable nodes in joint decoding, while they're usually avoided in single user decoding. Another difference to single user decoding is that while in single user decoding the order of degree 1 variable nodes, or variable nodes in general, is not significant, in 2-user asynchronous decoding the order of variable nodes is very much significant. For example, if we switch the order of these 2 variable nodes, we can see that we have effectively removed the 4 set. This means that not only is the order of variable nodes important, but we can even remove 4 sets by changing the order of variable nodes, and this is exactly how we propose to remove 4 sets in our paper. But first let us continue, and if the order of variable nodes is important, we can also look at the distance between variable nodes. And what we notice here is that a 4 set is made up of 2 pairs of degree 1 variable nodes. What makes these degree 1 variable nodes a pair is that they are connected to the same check node. And these 2 pairs of degree 1 variable nodes have the same distance between the variable nodes. Motivated by this, we define a D, which is the multiset of distances between degree 1 variable nodes connected to the same check node. Then we aggregate these distances over all check nodes to form this total multiset D. And using the distance multiset D, we could in our paper prove these 2 theorems, which in combination state that a parity check matrix H is 4 set free. That means in the joint graph, this parity check matrix leads to no 4 sets for any delay tau strictly greater than 0. So it is 4 set free if and only if the distances in D are unique. This means no duplicates. So if we want to find 4 set free parity check matrices, this is the same as finding distance multisets D with no duplicate entries. And one intuition here is that if we reduce the size of the distance multiset D, then we reduce the perceived risk of having any duplicates. Theorem 3 states that we minimize the size of the distance multiset D if we do what we call an even distribution of degree 1 variable nodes across check nodes. This What we mean by an even distribution is that each check node is connected to approximately the same number of degree 1 variable nodes, as you can see in the example. We can also prove this bound on which for which codes four-set-free parity-check matrices exist and for which not. It is in terms of L1, the fraction of degree 1 variable nodes in a code, and RD, its design rate. If the L1 RD point of a given code is above this curve, we can prove that there is no four-set-free parity-check matrix for this code. However, if the point is below, we cannot prove that there is a four-set-free parity-check matrix because we could not show that this bound is actually achievable. But we will see in the next slide that we can actually get reasonably close. So here, what we have on this slide, we now have the important part on how do we actually find a four-set-free parity-check matrix. The idea, as I teased earlier, is we want to permute the columns of the parity-check matrix. This effectively changes the order of the variable nodes in the tenor graph. If we change the order of the variable nodes, and we do this in a smart way, we remove any duplicates from the distance multiset D, and we have a four-set-free parity-check matrix. Our algorithm is essentially a greedy approach. It goes from check node to check node, and for each check node it adds variable node by variable node. For each variable node it randomly selects a location where it could add this variable node. Then it checks if adding a degree 1 variable node in this location would lead to any duplicates in the distance multiset. If this is not the case, it adds the variable node in this location. If this would lead to a duplicate distance, then it discards the location and resamples a new location, and it continues until it has assigned locations to all degree 1 variable nodes for all check nodes. Now, the outermost points in the L1R plane for which we could generate four-set-free parity-check matrices using this algorithm 1 are shown in the plot, and what we can see is that they are reasonably close to the bound we derived on the previous slide. We could try to improve this algorithm 1 to get closer to the bound. However, for 1, we do not know if the bound is actually achievable, and for 2, we can already create four-set-free parity-check matrices for all codes below capacity if the fraction of degree 1 variable nodes is less than 0.7. Any codes we found always have significantly lower degrees of lower fractions of degree 1 variable nodes. This means from a merely practical perspective, we do not see any reason to further improve our algorithm. Indeed, we actually came up with algorithm 2, which slightly reduces this L1R area which we can cover. So algorithm 2 repeats algorithm 1 multiple times until the returned parity-check matrix is free of all larger degree 1 variable node stopping sets for all delays tau greater than 0. Of course, if we look at the fringe of the achievable L1R region with algorithm 1, this will take increasingly many repetitions of algorithm 1 to find such a parity-check matrix devoid of all larger degree 1 variable node stopping sets, so the L1R area is effectively reduced. However, for most codes we looked at, this was not a problem. As I already said, most codes have significantly lower fractions of degree 1 variable nodes than what is possible to achieve with algorithm 1. So now let us look at some simulation results. What we can see here is the delay tau between the two senders on the x-axis and the error probability on the y-axis. And the code we are looking at first is constructed using progressive edge growth, which is a single user parity-check matrix optimization technique. However, it is not a two-user optimization technique. That's why the joint graph exhibits a four-set for the delay tau equals 4. This then leads to this relatively high peak in the error probability, and if in average this would lead to very high or this would significantly increase the error probability. If we then use our algorithm 2 to remove this four-set, we also remove the peak in the error probability, and now if tau would be random, This would significantly reduce the average error probability in the system. And such a system with random tau is exactly what we are looking at in this figure. Now tau is random between 1 and 50, and instead of tau we now have the block length n on the x-axis while the error probability remains on the y-axis. And we are first looking at a randomly constructed code. This has a relatively high number of for sets and other stopping sets, so we have this high error floor. If we then use our intuition from earlier and evenly distribute the degree 1 variable nodes across the check nodes, we get what we call even random code construction, and this can reduce the error probability by almost 1 order of magnitude for the higher block lengths. If we use instead PEG, we notice by chance that PEG actually also enforces an even distribution of degree 1 variable nodes across check nodes. But what PEG is actually designed to do is this single user girth optimization, and what we can note here is that PEG actually only achieves a marginal gain over just doing random code construction and an even distribution of degree 1 variable nodes. This means that the single user graph structure is significantly less important than the two-user graph structure for two-user decoding. Finally, if we apply algorithm 2 to remove all degree 1 variable node stopping sets for all delays tau greater than 0, we can again reduce the error probability by almost 1 order of magnitude, and what we can notice now is that the gain by using PEG has also increased because the most harmful two-user joint graph features have been removed, so the single-user graph features become a bit more important. So, what we started with was an analysis of 4 sets. We notice that if we are doing two-user decoding and we have asynchrony, then the order of degree 1 variable nodes and any other variable nodes is very important, while the order of variable nodes is not important for single-user decoding. We noticed, or we had the intuition, that an even distribution of degree 1 variable nodes may be beneficial, and then we also proposed an algorithm to remove all degree 1 variable node stopping sets for all delays tau strictly greater than 0. Then with the even distribution of degree 1 variable nodes and our algorithm, we could reduce the error probability for higher block lengths by almost 2 orders of magnitude. Thank you very much for listening. At the ISIT, this was a point where I received questions. However, the paper is now also linked in the description. This means if you go there, read the paper and have any further questions, you can drop me an email. There's the email link in the email address is in the paper, and I'm looking forward to any correspondence. Thank you.